Okay, so we go to the last lecture for the nuclear structure and short-range correlation. So based on the discussion earlier, I dragged some of the slides. I think it may be interesting for you to see. So when we talk about like NP dominant, right? So we are showing like this one from the lecture 3, the calculation from theory about like density, the density function of the NP and PP pair. So we know that we noticed that between 300 and 600, it looks like the contribution to the density from NP is much bigger than PP pair here. So that is the reason we believe that why the NP is dominant within this range. So this is from what we observe from the data, and so from the calculation. So now I want to show you that the result, we use that from the GCF, we just discussed this morning, to see how it describes its behavior as well. So actually from the GCF, we are using that contact formalism. We able to calculate the ratio of the EE prime PP on the EE prime P to ratio from the carbon 12. So the one I'm showing here is the function of this ratio as a missing momentum and using the AV18, and it calculates using that GCF like contact formalism. So as you can see that the contact formalism calculation can describe the data very well up to 1 GeV using AV18. So that is what Alex and I were mentioned earlier in the discussion. So this is really impressive because the 1 GeV initial momentum is really high. And you can see that the calculation and the data, they agree very well with each other. And the one thing you can see that is captured here is that this is an area where the dominant, right, around 300 to 600 MeV. So this is the area where the NP dominant and the PP is in that the deep one. So it means that this is where the NP is suppressed. So that is what you are really seeing here in this ratio 2. So you can see the ratio of the PP to the total number of EE by P is really low here, but then it's back up here. So it captures the transition really nicely, like what you are seeing here if you see back. So in these areas around here, you can see the deep here really low, right? So that is where the PP pair contributions suppress a lot, but then it's back up. So when you go to higher and higher the momentum here, so the difference between the NP and the PP is not completely dominant by NP anymore. So you can see the transition really well from the picture I'm showing you here. So it transitions from the where the PP is suppressed, and it goes to the area like when you go to higher momentum, that suppression is start decreasing. And here, so I show you in this area, it's a spin suppression PP, and now you will have it not suppressed anymore. So this is the calculation from GCF describe data very well, and it can capture the transition between from the tensor to the scalar one. And we discussed a lot in the lecture 3. And Alex also mentioned about like, oh, he have some idea about the why the AV18 to work well. And here is a comparison of the different calculation, the same thing, but using the different model. So you can see that the AV18 or N2LO here, they capture the data pretty well. And it depends on the cutoff of the N2LO. So you can see that they capture the data well, but depend on the different models, they have a different uncertainty band here. And then we also put one the extra guide outliner here, the AV4. So this AV4 one is the one it didn't include like any information about tensor 4 of the NP dominant at all. So as you can see that this one, it definitely is not we expected that this one is not working because it didn't include the behavior is suit for the transition here. And we do the calculation with A418, it's like a closer test. And we definitely see that if it not includes a tensor part in the ANN interaction, it will not able to capture the data. So that is like another kind of close test in order to see that, oh, this transition from the tensor to scalar is really described well in the calculation. Yeah. And I put out here is this work have been published on Nature. It is very high impact work in the 2020, in case you want to have more information about that. So with this one, I think we can just stop our discussion in terms of the quasi-elastic scattering for the SRC study. So now we are going to the next scale, is the substructure of the nucleon. So when we talk about substructure of the nucleon, it means that we are going to study the quark and gluon, the structure inside that one. So we mentioned from the very beginning of the lecture series, we need to use the DIS region if we want to study this substructure of nucleon. So this is a diagram to tell you a little bit more about how the DIS break up. So the breakup here, like this virtual photon, it will interacting with nucleon inside of nuclei. And then it carries the enough energy to break up this like one to the different particle we call particle shower. So the interaction here, it have a final enough the resolution in order to interact with the proton. When say proton here, it means the quark here inside of nucleon. So in this process, is the DIS process. So cross section, it will depend on what we call nucleon the structure function F2. And this one, this F2, it will help us to have information about what is the structure inside of this nucleon. And it can have some correlation with the F1 here. So you can think about it in terms of this cross section. You can write it in terms of one kinetic factor K here, and then the F2. And this F2, it carries the like structure information of this nucleon. So we can go from the very simple picture about what this F2 can tell us about the structure of the nucleon. Because the nucleon, inside this nucleon, we will have a quark, like quark and gluons are binding together is really complicated. So it's not just the purely it's just the three quark and combined with gluon together. It also have some kind of like quark, anti-quark, and create a C quark inside there. So it's very complicated. So if now we go from the very simple picture, what if the inside the nucleon is just have one quark? So what this F2 should look like? So then it will just be equal to 1, right? Because it's just one object inside this structure. And just to remind you a little bit here, so we can so this is just like F2 structure function. So you can calculate it as a sum of the electric charge of the proton square and multiple to the X. And this one is the proton distribution. It means like quark distribution, gluon distribution inside nucleon. So this is how we can form up the F2 and how the F2 related to the information of the different like proton inside nucleon. So the simple picture, one quark, then the F2 is just a constant, it's equal to 1, simple picture, right? But now we know that they have 2 quarks. So then what we expected it wouldn't be like, oh, it's about the 0.3 something, it distributes equally something. So this is what we can expect it from the F2. And then now we consider the binding between this quark, then by the gluon, then this binding with the broaden that distribution. So that is why we expected, oh, if in this case we will have this F2 is around 0.3, but it's a broaden one. But in reality, like I mentioned with you, that it's not the trivial like that, it's much more complicated. So we will expect it, oh, maybe F2 will have this structure. So
excuse me, can I have a quick question? So in the previous slide, if you can go there. So what the x-axis really means? What is momentum fraction?
A momentum fraction x. So this one, it is the fraction momentum carried by quark inside the inside nucleon. So the nucleon, they have a total momentum, right? So then the x here is a fraction of the momentum carried by quark. by that proton. So
vary
that
by
is
one specific quark. Did you mean to say that?
For a given one, yeah.
Oh, okay, great, thanks.
Yeah, so that is physical meaning. Yeah. So actually, the ZF2, it is the very intensive measurement in the, I think, few decades already. So this is everything we know. Like this is raw data about the F2 structure functions for the proton. So you can see that it's very intensive measurement. So it's in the 5 order of the Q square and in the very large range of the Acke as well. So we have a pretty reasonable the measurement in terms of the F2 for the proton. And like I mentioned that this F2 is connected to the proton distribution. It means that distribution of different components inside of the nucleon as well. So I also showing the picture on the right here is a global fitting to show you the distribution of the different term, like for the U quark, D quark, or gluon, or the C quark here. So this is using the some fitting in order to get the proton distribution here. I believe that some of the students in the school are doing a lot about proton distribution. I think it's the Melanie. Yep. So that shows you like where we are stand, and this is the picture about how the F2 and the PDF, the Fi, the proton distribution look like in general. So you have a picture of how they look. Yeah. So the question here is that we study about nucleon. So when we have a nucleon, we have two cases, right? So we have nucleon here, the proton and neutron. For example, like when they are stand alone, for proton, we can have a free proton, means that the proton stay alone itself. So we call it the free proton. We don't have the free neutron target, but we also using the measurement on some light nuclei like the deuteron or helium-3 in order to extract the structure of the neutron due to some like nuclear correction. So now the question you will have in your mind is that, so what is the F2 structure function of a nuclei A? So is that the combination of the, it's just the sum of the F2 from the proton multiple with number of proton and the plot with F2 from neutron multiple with number of neutron. So this is the question we want to ask. If this question, it will very much related to, it will depend on the quark move differently in the nuclei and the nuclear environment affect the quark. So the question in the simple way is that, is the free nucleon, let's stay alone, behavior in the same way as the bound nucleon inside nuclei or not? So that is the question we want to answer. So I have a question, like we should have some expectation first about this question. Is that when we talk about nucleon, it in terms of GeV, right? But now when we put this nucleon, like the mass and the thing of it is in the scale of the GeV, very big. And then now we use the nucleon to form nuclei. So we just put them together, they bound together in order to make up this nuclei. So the scalar chain is very separated scale. So these nucleon, they're just binding together in order to make this nuclei. And this binding energy is just in terms of MeV. So MeV to GeV, it's completely different scale. So it's so small compared to this GeV scale. So in naive expectation, how come this tiny binding energy can affect anything? So it means that with this naive expectation, we will think that the bound nucleon, the nucleon inside nuclei, will behave the same as the free nucleon. And only thing it could different here is the Fermi motion correction. Because when you have a nucleon inside nuclei, it's moving inside nuclei. And that one, they have a nuclear like Fermi motion in there. So if it's different, it only should be different by the Fermi, the motion correction there. And other than that, we naively expected that there are no different. But now let's take a look at one question, and I would like you to think about this a little bit. what is the simplest example of nuclear interaction? It affecting the platonic property. The simplest example, like give each other 1 minute and think about that. Like what example you think is simplest example in the nature is showing you that like when it nucleon inside nuclei, it changes behavior. Anyone have an idea about it? Yes. Yeah, just unmute and speak the direct. Yeah.
Oh, just kind of as a naive guess, I'm not an expert on how all the strong interactions work, but I know what because what binds the protons and neutrons together is like interactions between the quarks from like one proton and another neutron, because I know that other like measurements of the mass radius of the proton is different like for a bound proton than a free proton. So that kind of shows that the quarks are interacting with the other quarks from another nucleon. So that kind of shows that they're not just like I guess like a free gas bouncing around in there. They're talking to each other and interacting in that way.
Okay, yeah, that's right. Yeah, so the simplest the nuclei is a deuteron, right? So you can see that deuteron is the combination between the proton and the neutron. So when the neutron stay alone, like free neutron, it will quickly decay, like in within like 10-13 minutes, right? So that is free neutron. But now when it get bound with proton inside this simplest nuclei deuteron, then it change. It not decay anymore. It just stay with the proton and happy forever together. So from this very simple picture, we already can see that, oh, so bound neutron in this case, it have a different behavior compared to the free one, okay? So that is one of simplest picture. So keep it in mind, we have expectation that, oh, so binding effect, even if very small, but it can change the behavior of the bound nucleon compared to the free one. And then we really can see it from the data. So what data we are showing here is the cross section of the carbon-12 ratio to the ratio of carbon-12 to the deuterium. So we divide by 12 and 2 here is to average over the number of the nucleon. So this ratio cross section, it can directly compare to the F2 ratio of the carbon-12 to the F2 of deuteron. So if they are the same, they should equal to 1, just flat, nothing change, right? But in fact, you can see that they have a linear decrease here. So it means that it's different from the expectation that the bound nucleon are the same like the free nucleon from this picture. And what we determine as EMC effect is the between region of the X between 0.3 and 0.7 here. And the EMC effect, the sign of EMC effect is characterized by the slope, the linear slope between this 0.3 to 0.7. So when they talk to you about EMC effect, you know that is the linear decrease between the 0.3 to 0.7 of the ratio of the form of the F2 form factor here. So this one, so we can see the characteristic of the one nuclei only. And now it appears to be very universal behavior across the different nuclei. So this is like kind of like data detected from the SLAC in 1994, and the more recently either from the JLab with the much higher precision here. So you can see that within that area there, you can see the linear decrease, and that is the EMC effect we are trying to study, and it's across different nuclei. So now if you see, we want to study a little bit more about the EMC effect, let's put them all together. So this is the SLAC data. So if you put all of it together with the different nuclei, you notice this EMC effect is increasing with the nuclear mass here. So this is a picture in the different view, so you can see it a little bit better. So what causes EMC effect? We have no common accepted agreement at this point among theory and experimental. It is it's almost a 40-year question. And now we know that the EMC effect here is driven by the nuclear structure and dynamic. But what exactly causing this EMC effect? We don't have common agreement at this point. So many work have been done and so many assumptions to put into the EMC effect study. So there are one joke is that the EMC means that every model is cool. So because the normal model, it can convince everyone. So that is why we think about it like the funny joke between us, like, oh, everything is cool, everything is good. So there are many models I mentioned, and they have around 4 papers here. They have a very good review about what have been assumed about EMC effect. Many of them I'm not clear about that either in terms of the theory, but this is a very good overview about what have been assumed about EMC effect in the different type of model and how people trying to explain the EMC effect. But for this topic here, because we're talking about short-range correlation, I just want to show you one of the model. It tried to connect between the EMC effects and the SRC. So now we think about it a little bit slower in the picture we have learned so far, right? So for example, yes. You have a question? Yeah.
Yeah, I just had a so when you were showing the picture, because you were getting the slope of the from the EMC effect between like the X of 0.35 and 0.7.
Mm-hmm.
But one thing I was wondering is like why were all of them being fit to a straight line? Because if you like going back like a couple of slides to where you had like all of or all of the elements plotted on the same slide. I think it was the one.
Yes.
Yeah, that one. Because looking at that range, you can kind of see that not all of them are entirely linear over that same range. Some of them look like they start to kind of curve up sooner than others. So I was just wondering, like, I guess why make it all linear and not use like a higher order polynomial or some other function.
I see. So here, so if we take a look at this one, when you take a look at this range, you may see some of fluctuation here, right? That fluctuation is in terms of statistic as well, right? So I think like overall it's kind of like linear in my opinion, and this is like how we define it decreasing. I don't know if you ask me that why don't we use a higher the order fit, right? In my perspective, let me think. First, I think the linear is well described. Is it like, yeah, Melanie, you have another comment or something there?
It's another question about this.
Oh, okay. So let's finish the question first.
Yes.
Yeah. So I think first in this order, I think the fluctuation of statistic, it can be captured by linear fit well enough. And I think that it is not, in my opinion, when we perform the fit, it better to use simple fit if it describes the data better. If you try to go to higher and higher order, the chance you get the overfit is higher, and it's just like it just captures the noise. It's not really the capture of the physics there. That in my perspective of the fitting here. And then I think if the linear fit, I think it captures it fluctuation pretty well already, and it do reasonable work. And I think this is what they use to define the strength of this EMC. So that is my answer for you. Yeah. Yeah, Melanie. Yeah.
Yes, I just wondering why, well, what does it mean that after 0.7, the data increased?
Which one? Yeah.
In all the graphics, after 0.7, the data increased?
Yes, that's a good question. Yeah. So you see the structure kind of change, right? So from here to here, you see a degree, and you're asking me what created Z rise, right? Is that your question, yes, Melanie? Yeah. So that is the Fermi motion effect. Yeah. So here, like when we get to in this region here, so the Fermi motion is the one bring that one raising up. We can see it better from this picture actually here. So this one, when we connect them together, here's the picture I'm showing here, Melina. So you can see that now, whenever before we discussed about SRC, right, we just care about the region about X bigger than 1. So we only see data from this range. So now for the DIR, we are seeing the EMC effect from this low range. So the right you are seeing is right here, right? So it very much like it enters the region where the Fermi motion, it kind of plays the big role. So that's why from this modification, it adding the Fermi motion, it kind of brings that raise up. And then that Fermi motion, it also broadens it quasi-elastic peak as well. So that's the answer for your question. Yeah.
Okay, thank you.
Yeah. So, okay, we can continue here. So let me check the time, because I promised you guys that we have a 20 minutes to watch movie together. How much time do we have left? Yeah. Alex, can you tell me how much time we have left? Let me see.
We still have plenty of time.
Oh, that's good. We started
I would say half an hour.
Oh, good. So we have a 10 more minutes to talk about SRC and 20 minutes for the movie. Okay, so we on track. Yep.
Yeah, so the nominal time is until 11:15 actually. That's half an hour for the lecture. But then after that, we have also a half an hour slot to discuss. Okay, good. Yeah. Yeah, I forgot to track the time. Yeah, so now we talk about one of the potential model, or I can call it the hypothesis that can explain the EMC. It's one of many. Okay, I think that there are many of them out there, but you can go to the paper to review about that. I don't, it's too many to discuss in the lecture. We will not have enough time for that. So now we think about this picture. It seems to be universal behavior of the EMC effect across all the nuclei. And when we think about SRC effect, it also behavior very universal between different nuclei. So it kind of like clinking on our head and things like, oh, is it universal? They are something to do with each other. Is there any way we can connect together? So that is why we start putting the picture of the EMC and SRC on the same picture together. So, oh, these are universal, but they're on the different scale. One is in terms of nucleon scale, one is a subnucleon scale. So there are any connection there. So then in order to see connection between them, if they have something connected, they will be correlated, right? So that is the idea we have in general. And they indeed have some correlation. So when we put together the connection between EMC effect, so the EMC effect, like I said, explained to you that it is determined by the slope of that F2 ratio between 0.3 and 0.7, that linear slope right there.
So that is the EMC effect in the y-axis here. And what is the property to describe the SRC is A2? I don't know if you still remember that. So A2, I remind you if you forget about that. So the A2 here is in the area where the short-range correlation is the dominant. Then it is ratio of the cross-section, and it's shown at the plateau here. So the value of this plateau is characterize the SRC. So we call it A2. So when we plot the EMC slope and the A2 together in the same plot, so you can see that there are linear correlation between them. So that is when the thought becomes more clear, or it looks like they have some correlation between some connection between the two of the effects, SRC and the EMC. So the question is that for the EMC effect, it means that like what we are thinking EMC is the bound nucleon is modified by the nuclear effect, right? So the question is that EMC is related to this high momentum nucleon in the SRC, and is a high momentum nucleon modified? So now the big question is that you have in the nuclei, you not just have SRC. You remember that you still have a mean field nucleon as well. So now the next question we want to answer is that, oh, so all nucleon make the total modification on nucleon, or only few of them, what are in the, can you still hear me? It looked like I lost connection.
Yeah, sorry, can you repeat those last few sentences?
Yeah, I think we missed you for 1 minute.
Okay, I lost the connection. Okay, let's start from the slide again. So there are a question, the biggest question about EMC effect is that we noted that it have a modification of the nucleon inside nuclei. So the question is that is all nucleon, they modify the same amount, and all of this one combined together to make total modification of nucleon inside nuclei, or only few of them modify? And is it few modified nucleon, it comes from SRC, and it which way it should be? So we come up with what we call Emc Src model. So the hypothesis in this model is that the EMC effect is being due entirely due to modification of SRC pair. So like it only modify when it in the SRC pair, like only when it have high momentum, then it modify. So this is the hypothesis of this model we are working on. And you remember one more thing, one characteristic of the SRC is that the SRC is isospin dependent. It means that like it completely dominant by the NP pair. So if combines the two of the assumption, we think, oh, if EMC effect is being due entirely to SRC, so that will be due to NP SRC pair because they dominant. So the picture that, okay, so the one here maybe
Did everyone miss the audio?
Yeah, I can't hear anything.
Okay, so yeah, let's wait for it to return.
SRC.
Oh, Dien, I'm sorry, like we missed you for a few minutes, I would say.
Oh,
like,
you lost me again?
Yeah, so if you could go back to the previous slide there. No, I guess we got the thing when the...
Did we get through this one?
Yeah, of course, in the next one, yeah, as well, but not the transition. Like we we got about the high momentum dominance, like when the EMC effect kicks in, but then we missed you.
Sorry, my internet is so bad this morning.
It's okay, don't worry. We will let you know.
Okay, so we repeat again here as well. Yeah, so in Z-like Emc Src model, the expectation is that Emc is only due to Z-like NP Src pair. So we know that like NC dominant is the universal and Src behavior is universal across different nuclei. So then if the Emc effect, it really comes from Src, it should able to describe by a universal function as well. So that is simple expectation. So with Emc model, we will expect it, like I just mentioned, it predicts that modification of Src should be universal. So now let's go step by step to see is that really can describe by a universal function. So if we assume that the modification only comes from the Src pair, right? So then we can write the F2 function of the nuclei A in terms of the number of proton for F2 of proton, number of neutron with the F2 neutron here. And then this one is unmodified, it's just the free one. So all the modification, it will come from the Src pair. So this is the number of NP Src pair in the nuclear A, and then this delta is present for modification of the F2P and the F2N here. So this is modification part. Similarly, we can do exactly the same for the F2D. So it will equal to the sum of the F2 from proton, neutron, and the modification depend on the number of the Src in the neutron as well. So this is the simple way to get to this F2 based on this assumption. So now what is Emc effect? How you get Emc effect? So Emc effect is determined by the ratio of this F2 per nucleon, right? So you have this F2A and F2D, then you will take the ratio of it, divide by number of nucleon. So this one is what you can measure in the experimental, and you can see it as Emc effect. So with some math, doing some math, we can convert this ratio from the two ingredients in terms of this one, this formula right here, where the A2 is the ratio of the number of Src pair in nuclear A to the number of Src pair in the neutron. So I will not go to math from here to here, but I think it's pretty straightforward to go from here to here. So when you take a look at this formula, you will see that, oh, this ratio is showing you the Emc effect. And then this one, you also can measure it in experiment. Yep, it is like for neutron. One thing we want to use the ratio of proton to neutron here, because we don't want to deal with the nuclear effect of the F2N, because I mentioned with you that the neutron is not the free neutron. So if we use something related to F2N here, it will be some nuclear model dependent as well. So that is why we are using the Z ratio. It can get out directly from the measurement as well. So you have all these numbers and you can get A2 from Src measurement. So only thing left is in Z green box right here. So that is nuclear independent. So now we have all ingredients in this formula here already. So you can take the whole model, get into the one equation only. And if from all the other ingredients, we can extract it, this nuclear independent right here, equal to this formula. You have everything to extract this one. And if this function is showing the universal behavior across different nuclei, then we're saying that this SRC EMC model really can describe by SRC. That is the idea. And then this is what we see in the data. So for the data, we do measurement, EMC effect measurement of many different nuclei. Each of the line here is related to different nuclei. And this one, the special one here, we still need to learn about it. I believe that it is helium-3. This curve is completely different compared to other curve. And we still need to understand exactly what it makes it so different compared to the other one. So we have EMC data. Beyond it, like EMC, like slope here. And then you will have all other ingredients, and you will calculate this U1 based on the previous slide formula. And actually, when we calculate that U function is right here. U here is represent universal function from different nuclei. So you can see that all of this different here is collapsing really nicely when you look at this universal function. So all the nuclei, even including this weird guy here, so you can see that they're almost collapsing to one of the function here. And we can use this one as one of universal function in order to describe this EMC effect for different nuclei. So from this result, it was published like, I think 3 years ago. So you can check that out. So this is really big result, and it can give us some hint about, oh, maybe we can use SRC in order to explain the EMC effect. Because from our study, we can see that EMC effect can be well described by this universal modification of the SRC pair function. But this hypothesis still need to put into test more in order to confirm that, oh, this EMC effect, it really comes from the nucleon in SRC. So we have a very comprehensive experimental program in order to test the EMC SRC effect further in the JLab. So with that program, we're using the different type of measurement. What we use now is the tag DIF on the neutron. So the tag neutron is different with what we have been discussed so far. So what I mean by the tag measurement. So the tag measurement here is that we will have so far what we discussed about EMC effect, that is EE bright DIF, right? So on EE bright measurement, we only detected scattered electron and take the cross section, take the ratio in order to extract it, the EMC effect. So we have very little information about what nucleon is struck on. So now in the tag DIF, we will detect the recoil particle. So we will, for detect this one, and on neutron, it only make a proton and neutron, right? So if we able to detect the recoil one, we will have information what is the struck nucleon. So for example, that if we struck neutron on the recoil, we will know that what is interaction is the proton. So, and on other side, if we detect the recoil proton, we know that nucleon in the interaction is the proton. So with the tag DIF from the neutron, we will have a much more information about what is the nucleon in the interaction to study the EMC SRC effect. So we also have the model. We have the model for the prediction for the if the EMC come from SRC effect. So we will take the ratio of the bound F2 to the free F2, and we can have that prediction. So now we will do the DIS tagging measurement in order to compare with the measurement here. So the idea is that if the data it really agree with the SRC prediction, SRC model prediction, we will have confidence to claim that SRC is the reason for EMC effect. So the first experiment we have a JLab, we call the band one. So for the band, what we detect is the recoiled proton here. And for this experiment, data already been taken and it under analysis at this point. And we expected the result will come out soon. And another one is like sister experiment compared with this band experiment in the lab. So in the lab experiment, we will detect the recoiled proton as well. So by combining the data from these two experiments, we're hoping to nail down our SRC EMC effect theory. So this is some projection of the data, like how well, like how much statistic we can measure in this experiment. And we have one part of data already, blue already, and we waiting for the red one. So I think this will be really big result as well. And it will be like ground play for us to see if we can claim that EMC effect comes from SRC. So stay tuned and we hope to have results to share with you on this study very soon. So with it, I think I want to close our lecture here with one of the slides. So I hope that by now you have some idea about what SRC is and what we have learned about SRC and some of the very exciting results from SRC in last few recent years. And in the final, I would say that SRC it has many implications. We're only able to touch base in some of the topic here, but indeed it has a much more implication. And this field is evolving really fast, and it has a lot of connection with other field. So after this talk, at least I hope you think that SRC is interesting, and if you have more questions or interested about how SRC work and how it related to what you are doing, it will be great for discuss each other about that. So with that, I would like to take questions right now. If you have questions, or if you are too tired with SRC, it's too intensive, we can take a break, watch a Proton movie, and then in the informal discussion, you recharge after some fun, and you can ask me any question you have. So whatever way you prefer.
Thank you very much, Dien.
So,
and can I ask?
I guess we have some question from Erin.
Yeah, sure. Yes.
Oh no, I was just clapping.
Okay, sure. Thank you. Phoebe, have a question?
I'm sorry. I get so confused with like hands raised or clapping.
That is Zoom effect. Don't worry about it. We will find out.
But we have some questions.
Yes, Phoebe.
I was wondering if you could speak more to how SRCs relate to neutron stars. Because that's like a selling point in my research, but I don't really understand the connection, I guess.
So this is in my humble opinion and in my limited understanding about neutron star, I can share with you some perspective, the general idea, okay? But then in detail, you might need to dig down in some reference, okay? So what the neutron star really study in my perspective is that it's really dense system. And what I want to study is relationship between the mass and the radius of the neutron star. That is like equation, state equation. So that is relationship between the mass and the radius of the neutron star. So in this equation of state, it depends on the momentum and energy distribution inside the neutron star. So before, like if we don't include this SRC effect, because in the neutron star, they think about it like 90% is the neutron and only like 95 neutron and only 5% is the proton. So we house it like SRC, the SRC like dominant of NP. So the distribution of the neutron star very much like it, like you think about it like a shell, right? So proton is have a very little, so they only occupy the area with the small like momentum energy. So the getting out there is depend on the neutron distribution. But now when you include the SRC pair, it will change how the momentum distribution distribute in the neutron star, because now though the proton will get out like combined with that 95% of the neutron, then they can create the NP pair and like what we see in SRC, right? So it means that these proton, they may not just stay in that tiny corner and carry the momentum and energy anymore. They may spreading around and carry and contribute much more than they expected. So all of that behavior, it will affect how momentum and energy distribution in the neutron star. It will change that distribution. And that distribution, it will get into the equation of state in order to calculate the other property of the neutron star, right? Because it like input for all other calculation. And if that input change, it will affect all other calculation as well. But how big is the effect? We need to see, like do more study and see, oh, if I add that effect in, how big it will change the output of the neutron star calculation, neutron star study. Yep. I hope it help you. Yeah.
Yeah, thanks.
Mm-hmm.
Thank you, Dien.
Yeah.
I see one. Who is this? Okay, Matthew. Yeah.
Yeah, just a comment maybe on the neutron star question. Since the neutron star are lower neutron than proton, the neutron-neutron pair is, I think, no more too small to take in account. I mean, they're important in this. They are probably important in this case.
So yeah, that is why I say earlier is that we need to put into account of this SRC SRC effect, right? And then estimate how big the effect is. So we know that it will change, but how big the effect, I cannot have a quantitative number at this point. So you may be right that maybe because of it's just 5% and it's combined with like NP pair, even all of them combined to be NP pair, you may concern that effect cannot be big enough, right? But how big is that? We need to quantitatively calculate that first. Yeah.
Good. Any more questions? Please don't leave, because I think Alberto also wants to make some announcement here. So take this chance to make more questions.
So I guess that we can start with like what I mentioned. I really want to emphasize this one too.
Is this the animation that went like that? Oh my goodness, they released these days like.
I think that it released very shortly, like very recently as well.
Yeah. Ah, okay. So it's
and
nice.
this is because of this one is the project in making, like it is a huge effort from the both JLab and MIT, and from the Professor Richard Miner, one of the great scientists I get the opportunity to work with, and then like some of the other great scientists like Josida and Rolf N from the JLab side as well. I really think that they put a lot of effort and their mind into this project, and I think it's really useful.
I'm going to try to share this from here. Please let us know if the sound is not coming through. We'll give it a shot.
When we stand on a bathroom scale, we learn, for better or worse, our weight. In more precise terms, the scale quantifies our mass. All matter in the visible universe has mass. It's what governs the movement of planets, stars, and galaxies through the force of gravity. And all matter everywhere is structured in the same way. The Standard Model of Physics, developed more than 50 years ago, explains this structure in terms of quarks, gluons, and their interactions. These particles, interacting together, make up protons and neutrons, which along with electrons, in turn, make up more familiar atoms. But this creates a question. The mass of quarks inside a proton is much less than that of the proton itself. And gluons have no mass at all. How is this possible? In order to find some answers, we have to dive into the world inside the proton. But this presents a challenge. Protons are made up of chaotic bundles of quarks and gluons, moving at near light speed, interacting and annihilating each other. It has always seemed nearly impossible to create an accurate picture of this world. But a new collaborative project is visualizing the fundamental structure of the proton based on original research and sophisticated animation. Visualization has been a powerful tool for science for the last 3 decades. The Hubble Space Telescope has produced stunning images that have transformed how people everywhere view the universe. Now, a startling new view of the subatomic world is also within reach. Physicists from MIT and Jefferson Lab are working with a group of animators and documentary filmmakers to both create a more accurate visualization of the structure of the proton and to document the collaboration between science and the arts that drives this work. The goal is to provide a more complete view of subatomic structures that has the potential to change how people think about the nature of matter itself.
I've created the 3 quarks as points of light, and I've given them each a chromodynamic color, and I've set it up so they trade colors between each other the whole time. They're also moving in a way where they're jumping around.
Yeah, no, I think this was very good, the way you did that.
Yeah.
Visualization has long been used to help explain and understand the subatomic world. And these pictures have become more sophisticated as our understanding has improved. The ancient Greeks believed that matter could be split in more and more parts, until in the end, what was left were the smallest indivisible constituents, or atoms, from the Greek word atomos, which means indivisible. At the end of the 19th century, scientists learned that matter can be deconstructed into molecules, comprised of atoms. However, the choice of the word atom was premature. In the 20th century, we learned atoms can be deconstructed into electrons and their nuclei, comprised of protons and neutrons. And eventually, that every proton or neutron contains 3 primary quarks that define their separate identities. Often, constituent parts of all matter are portrayed as being shaped like round billiard balls, or in the case of quarks, as balls within the larger ball of a proton. We add squiggly lines, arrows, and other shapes to denote the forces at work at the quantum scale. While these diagrams can help explain what's going on, they in no way represent the reality of what this quantum world is actually like.
Referenced image that is in your slide deck is, I look at that and I have no idea what's going on in there. I see little, balls with up arrows and down arrows and squiggly lines.
In the proton, the quarks are held together by a force where gluons are exchanged, and with such a strength that the quarks and gluons cannot be isolated. The quarks and gluons carry a new quantum property known as color. The theory used to describe this force is known as quantum chromodynamics, or QCD, the quantum theory of color. There are 3 types of quantum color, called red, blue, and green, in analogy to the primary colors of visible light. All observable systems of quarks and gluons and their associated antiparticles found in nature are predicted in QCD to have equal amounts of red, blue, and green color. That is, they are colored white in analogy to visible light. Quarks do not actually have these colors, but just as white light can be divided into different colors, so can quark systems be divided into equal amounts of red, green, and blue. When we enter the quantum world, particles that are confined to small volumes move at near light speed. Everything is in continual motion. Gluons transform their energy into pairs of virtual matter and antimatter that are continuously created and destroyed, creating a quark sea, their existence exerted on other particles as a pressure. In this strange quantum world, conservation of energy can be temporarily broken, and even massive matter-antimatter pairs can live short times. Yet order also rules. Each elementary particle has a quantum property known as spin, which behaves like an intrinsic angular momentum. Nature's rules for spin provide order to the visible universe and is the reason for the periodic table of the elements and the shell structure of nuclei. To learn about the underlying structure of matter, scientists often rely on microscopes. In a microscope, light scatters from the object of interest. The scattered light is focused, detected in the eye of the viewer, and processed in her brain. The process is non-destructive in that the leaf or insect is not affected. With our eyes, we can readily discern structures of very large scales in the cosmos to human-sized scales of a meter, down to scales of 10 microns, as for example, a layer of the familiar kitchen aluminum foil. The ratio of such aluminum foil to a meter is down by a factor of 100,000. Scaling down with another factor of 100,000 gives the size of an atom, which we can see with powerful electron microscopes. One needs to scale down with yet another factor of 100,000 to come to the size of a proton, less than 1 femtometer, or 10 to the minus 15th meters. To see inside matter at this tiny scale, we use electron accelerators as microscopes. Hera was a particle accelerator located at DAISY in Hamburg, Germany, operating from 1992 to 2007. Hera was the world's first, and up to now only, collider facility of electron and proton beams, and discovered that gluons dominate deep inside a proton. Jefferson Lab, located in Newport News, Virginia, uses intense and polarized electron beams to impinge on fixed targets of protons and heavier nuclei to make precise maps of matter in a region where a few quarks dominate. A major new accelerator, the Electron Ion Collider, or EIC, is being developed in the U.S. to be located at Brookhaven National Lab in Long Island, New York, and it is anticipated to start operations in the 2030s. EIC will provide precise maps to bridge the regions where a few quarks dominate the structure of protons and nuclei to where gluons dominate. The goal is to provide us with an understanding of the internal structure of the proton and more complex atomic nuclei that is comparable to our knowledge of the electron structure of atoms, which lies at the heart of modern technologies. What if there were no gluons and quark-gluon interactions? Your mass and the mass of the visible world would drop by about an order of magnitude. The MRI technique is based on using a high magnetic field to reverse the spins of the protons in the body. Without gluons and quark-gluon interactions, the signal strength would drop to 20% of its value. Indeed, without gluons, there would be no nucleons, no atomic nuclei, no visible world. Is it science fiction to believe understanding this miraculous quark-gluon structure of nuclei can lead to 21st century applications? No, as even if the internal structure of protons and more complex atomic nuclei reside in a quantum world with light speeds, with ever-changing numbers of particles, and with strong interactions, ultimate knowledge of this world will lead to the future of modern industry and medical applications. An example is given by modern computing that relies on our knowledge and ability to manipulate the quantum world. How do we learn about this strange world with electron accelerators? Like conventional cameras, how our accelerator sees its subject is governed by two adjustable parameters: resolution, or pixel size, and shutter speed. The resolution is correlated with the energy of the device. To probe substructures of the proton with its 1 femtometer size, the electron must be moving very near light speed. The negatively charged electron interacts with the fractionally charged quarks inside the proton by exchanging a photon, the quantum of electricity and magnetism. This photon exchange can keep the proton intact, but more commonly smashes it in pieces. Google Earth, in zooming from the Earth's radius to the MIT dome, increases the spatial resolution by about a factor of 100,000, the same factor we saw earlier that successively brings us from a human height to the thickness of household aluminum foil, then to the size of an atom, and finally to the radius of a proton. The shutter of a camera is a door that opens for a definite time to allow selected light to reach the medium. This time can, for our accelerator, also be determined from the electron and the proton and can be equated with the value of Bjorken x. X can be interpreted as the fraction of momentum of the proton that is carried by the struck quark. Mostly based on a large data set from the only previous Electron-Proton Collider, we have accumulated snapshots of the charged structure of the proton taken in a special boosted reference frame, where 1/x represents the shutter speed and 1/q the spatial resolution. QCD prescribes an evolution with q², which connects quarks and gluons. The animation shows the quark and gluon momentum distributions derived from these data. Note that the gluon, G, and C quark, S, distributions are reduced by a factor of 20 in these graphs. In a regular microscope, we use light to scatter from objects to magnify such that we can see them with our eyes. This light does not disturb the object, as we see it as is. This is not true for our high-energy electron scattering microscope. As an artifact of the special reference frame used for interpretation of the scattering experiments smashing the proton apart, we have gathered knowledge about the one-dimensional momentum fractions of quarks and gluons inside them. We have also gathered knowledge about the transverse spatial size of the composite proton from elastic scattering where the proton stays intact. This is important knowledge, but limited. Due to these limitations, it has been difficult to portray the inner structure and dynamics of the proton. But what do the data tell us? For the first time, we have constructed animations to illustrate the proton structure as a variation with x and as a variation with q². If one views deep inside the proton with fast shutter speeds or at small values of Bjorken x, its structure is dominated by gluons. Gluons split in more gluons, and two gluons can recombine into one, causing much activity or dynamics. Viewed with more modest shutter speeds, the process where a gluon creates two quarks, one quark and one antiquark, can be seen. Such a fluctuation is the root of what is termed a quark sea, and is, for example, responsible for details of the inner charge distribution of the charge-neutral neutron. Viewed at slow shutter speeds or at large Bjorken x, the proton structure gets dominated by three effective blobs, which carry the valence quark identity of the proton as being two up quarks and one down quark, confined together in a single proton by the exchange of gluons. What do we see when we peer inside the proton while increasing the spatial resolution q² of our camera? The answer depends on at which shutter speed x we are looking. At small values of x, we see more detail appear with increasing q², but we also see more and more gluons appear due to the specifics of QCD. The observer will have to distill this information from what appears a squashed, pancake-like proton due to the relativistic effect called Lorentz Contraction. At medium x, we see again the details increase, and both the density of the gluons and quark C increase with q², the gluons faster. At high X, we see a coarse structure reflecting 2 up and 1 down quarks, a structure that becomes more evident at higher Q squared, with also more gluons and quark C appearing with Q squared as driven by QCD. But again, the squashing of the spherical proton into the pancake-like objects complicates the ability of the observer to extract the proton structure and underlying quark-gluon interactions. By varying the pixel size and the shutter speed of our electron accelerator camera, we have gathered information about the proton structure over the last 5 decades since the discovery of quarks and QCD. We learned about the transverse spatial size of the composite proton and the one-dimensional momentum fractions of quarks and gluons inside them. However, large gaps of understanding remain. For now, we have used our imagination to fill this gap and animate what the data tell us about the 3-dimensional structure of the matter deep inside us. But much better, QCD theory developments over the last 2 decades now provide the foundation to extract these 3-dimensional pictures of the structure from select designer electron quark scattering processes. To accomplish this, we need a microscope with sufficient intensity to capture these designer processes and image the structures at the finest quark-gluon levels, to charter the rapidly moving gluon oceans, quark seas, and primary quark continents. The residue of the quark-gluon interactions in individual protons and neutrons leaks out and creates sufficient nuclear binding to pack protons and neutrons tightly together in tiny atomic nuclei. These act well beyond a mere collection of protons and neutrons and are much more dynamic, harboring mysteries as telltales of the underlying quark-gluon world. And vice versa, the behavior of quarks and gluons is expected to be entangled with the structure of the nucleus they reside in. Massive computer simulations indicate exotic gluons may be exchanged between individual protons and neutrons. The nucleus can also act as an amplifier and pack so many gluons together that no more fit, leading to saturation of the interactions. For the first time, we have developed a new animation-based framework in which to communicate, understand, and explore the fundamental structure of matter for the curious mind. These first-generation animations are based on current understanding and available data and seek to capture essential aspects of the strange and beautiful quantum world of the microcosm. But many mysteries remain in how the visible matter in the universe is constructed from elementary constituents. We now are working on a 3D visualization of these animations, and then we'll continue our journey to animate the nucleus.
Very nice. So nice.
Yeah, I hope you all enjoy the movie and think about Proton is like more beautiful than before the movie, if it's possible.
No, it's very nice, this video. The one that I saw was just the animation of the Proton, like not the whole video explaining everything. So very nice indeed.
Yeah, I think the scientists and filmmakers, they put a huge effort to make this movie. So I think it's a very good way to see a proton in a more charming way instead of the heavy math formula. So thank you very much again for all of you. I really enjoyed the experience to be with all of you for the Hug School, and good luck with your next step in your PhD program. Yeah, and stay in touch. If you have any question and more question about SRC, feel free to email me as well. Even after Hug School, I will be happy to be in touch and discuss with you about anything. Yeah, thank you very much.
Okay, thank you, Dien. Let's all thank Dien for her amazing lectures and everything. Thank you very much. It was a pleasure to have you here.
Thank you very much.
Thank you.